Welcome to our Quantum BW colloquium. My name is Niklas Schillo. I'm part of the team Quantum Computing at Fraunhofer IAO, and I will guide you through today's colloquium. So Quantum BW is a state initiative for quantum activities with the goal of bringing these activities together and creating an umbrella brand to promote those networks and activities, and also to increase the visibility of Baden-Württemberg as a quantum technology hotspot in Germany. And the goal of this colloquium here is to promote the scientific exchange between hardware topics and also algorithmic topics in the field of quantum computing, and to present the latest developments in this scientific field. Yes, and today I have the honor of introducing Professor Dr. Markus Müller from RWTH Aachen University and Forschungszentrum Jülich. In 2011 he completed his PhD under the supervision of Professor Peter Zoller at the University of Innsbruck and Ikurkrai, and from 2011 to 2015 he was a postdoctoral researcher at Complutense University Madrid, and after this in 2015 he became a senior lecturer in physics at Swansea University in the United Kingdom, and following this in 2018 he became a professor at Swansea University. And since 2019, he is now a professor for theoretical quantum technology at RWTH Aachen and Forschungszentrum Jülich. And yeah, we're very happy to have you here today, Professor Müller. And he will now give us an introduction to topological quantum error correction with his talk called The Dawn of Quantum Fault Tolerance. And in this talk he will first give us an introduction to the basics of quantum error correction, and following this he will present a recent progress in the area of topological quantum error correction based on new theory concepts and also some experimental breakthroughs. And if you have questions during the talk, especially online, please post them in the online chat. I will read them later. And with that, I will hand over to you, Professor Müller.
Thank you very much for the very kind introduction. Very warm welcome from my side. I'm very glad to be here. Thank you for the invitation. And as Niklas already pointed out, I would like you to take you onto a tour into the world of quantum error correction. And what you see here is kind of a cartoon version of a small basic quantum error correction code. And I hope that by the end of my talk I will convince you that these objects now start to fly, and that we are at the moment where we can start to scale up systems, and where hopefully you will see that quantum error correction is not something starting in 20 to 30 years, as you very often still hear, but something that starts to be useful even already today. A few words about us in Aachen and in Jülich. We are based there now for about 5 years. And there's a lot of activity going on in the wider area of quantum technology. In my group, we are focusing on quantum error correction and fault tolerance, but also quantum simulation, open systems, with a focus on AMO systems. That's where my background is from, but also with solid state systems. And then there are other research groups, both theoretically and experimentally, that also focus on other approaches, for example, on more explorative research on Majorana qubits or semiconductor spin qubits. All right, I think probably most of you know this, but just to kind of set the stage, we're interested in quantum computation. This is kind of a theorist's point of view of what a quantum computer looks like. We want to realize quantum computations on a register of qubits, and we do this typically in the gate model, where we can decompose a quantum computation into basic gate operations on single qubits here, as well as entangling operations between qubits. And the point I want to make is that as you all know, there are certain gate sets that are universal. For example, a Hadamard T gate on single physics qubits and an entangling C0 gate to create entanglement between qubits, and from those operations, from this discrete set of operations alone, we can approximate an arbitrary quantum computation. That means freely programmable our quantum computers. Why do I insist on this? Because we'll come back to these gates, but not on physical qubits, but later actually of how we can realize them also on error-corrected logical qubits. Why should we build a quantum computer? I think you don't have to convince you that this is a useful machine if you can build it in a large enough and error-robust manner. Perhaps the most famous application is factoring, which really kick-started the field with the discovery of Shor's algorithm to do this efficiently on quantum computers, whereas classical computers need an exponential time in the size of the numbers that we want to factor. Then there's classes of algorithms that are based on search. It's not only about finding some element in a database, but actually there's a very generic type of algorithms where we can speed up essentially the search for solutions to any problem where we don't have better strategies than just having a brute force search. And then perhaps in my opinion the most promising direction is quantum simulation, also from a scientific point of view, but not only, where we can use quantum computers as digital devices, which we can use to simulate the ground state properties as well as dynamics of complex many-body systems from a range of fields, including quantum chemistry, material science, or even high-energy physics in other fields in science, but also to use them in the field for optimization for real-world applications. At the moment, there's a kind of race going on between different platforms that try to build actual quantum computers, and we come back to some of these platforms in more detail later on. What you see here are ion trap quantum computers. On the right side, you see here a cartoon version of a neutral atom-based quantum computer with atoms sitting in optical lattices or tweezer arrays, each of these green points corresponding to an individual atom. And here on the lower part, I've showed two examples of solid-state-based approaches, such as superconducting qubits, as well as, for instance, spin qubits or other solid-state approaches, such as NV centers and or to be developed Majorana qubits. And at the moment, it's kind of not clear which platform will win this race. But what we are observing is that at the moment, a lot of efforts are ongoing to use these current prototype devices that we have already to see whether we can use them despite these devices still being quite noisy, to kind of run some useful applications and perhaps have some near-term quantum advantage. And the setting here is that we essentially have these devices of a few tens or now even a few hundreds of qubits, as we will see, and we try to run our quantum algorithms directly on this hardware, perhaps applying some additional techniques to kind of suppress some errors, to squeeze out, if you like, the best we can. But that is pretty much the kind of approach here. And with the paper on quantum supremacy from a few years back by Google, kind of this race to use these quantum devices for something useful became more apparent, also to a broader public, let's say. And what Google showed is back then on a 53-qubit superconducting quantum processor that they could run essentially a completely useless but random algorithm just to show that the output of such a quantum computation could no longer be efficiently simulated on a classical computer. Of course, there's an ongoing race also with numerical techniques that try to catch up and also push the limit. For instance, here I show an example of a work by IBM from last year, where they looked at some kicked easing model. The details are not so important, where they also claimed that one could already use these near-term quantum computers to simulate dynamics beyond what can be done numerically. In this case, I think it took a week or so until a kind of first theory group came out to show that they could actually simulate also these systems. So you see, this is an ongoing race, but what we actually know, and this is where I want to go to, is that where it's unclear at the moment where NISQ devices will be useful, we have strong, let's say, evidence or confidence in that we will have a guaranteed quantum advantage, at least for certain problems, if we can build large enough quantum computers, however, in a fault-tolerant regime. So what you see here is essentially a little map where I have here on the x-axis the number of logical qubits that we need for some algorithm, yeah? And here is the number of logical T-gates. We come back to these later, but you can think of these as the non-trivial gates to be performed in a logical quantum computation. And what you see is then really to have a guaranteed advantage, for instance, in cryptography or in quantum chemistry, we have to have control over several hundreds or even thousands of qubits, and importantly, to run gates in the area of millions or even billions of these non-trivial gate operations. And now we can ask ourselves, well, can we get to this regime with NISQ? And for me, I think the answer is quite clearly a no, because if you look at where current physical error rates on devices are, they are at the 10 to the minus 2, 10 to the minus 3 level. Yeah, in one physical gate operation, for instance, one in a 1,000 only fails. That's quite amazing experimentally. But in order to be running an algorithm with millions or billions of gates, we need kind of 1 over a million or billion as logical error rate on our operations, so that our quantum algorithm still spits out something that is not just noise. Yeah? So we need to get deep into this regime where error rates can be really suppressed by orders of magnitude from where we are experimentally now. What this makes clear is that the only kind of known path of how we can definitely get there, to the best we know as of today, is by using quantum error correction. And this is why I want to take you now onto a tour and kind of correct this wrong counting here from 1 to 5, yeah? Introducing 2 additional layers here, namely where the philosophy will be that we want to understand of how we can run quantum algorithms, but no, not directly on physical hardware, but on so-called logical qubits, which are collections of qubits, so-called quantum error correcting codes. And then the idea is that these can be protected by means of quantum error correction. And we have to see of how we can not only realize quantum error correction, but also logical quantum gate operations as we know them from the physical gate operations that we are used to realize on physical qubits. And this brings me to the outline of what I want to speak about. I want to give you a little bit more detailed introduction to quantum error correction codes and then topological toric or surface codes, and then tell you a little bit on progress on addressing the so-called quantum memory challenge of keeping encoded error-protected quantum states alive, but then also on the quantum processor challenge, as I call it, namely of doing non-trivial and eventually universal quantum gate operations on logical qubits. And then time permitting, I will comment on how we can scale systems up and also some new unconventional approaches towards building scalable error-corrected quantum computers. All right, then let's jump right away into the first part. And we start out with a very basic example, as basic as it can get, namely the 3-qubit quantum error correction code, which you see here. So the idea is that we want to store quantum states of a physical qubit, now not in individual physical qubits, where errors will directly destroy the information, but in a collection of qubits. Here, for instance, in 3-qubit states, yeah, where a logical 0 state would correspond to being all qubits in a 0 state and a logical 1, all qubits being in the 1 state. And now we can look at this a little bit more formally within the so-called stabilizer formalism. And this means that now in this Hilbert space, in this case of 3 physical qubits, we can define operators, check operators, that check for the parity of subsets of qubits forming our code. In this case, what we want is that the parity, for example, of the first and the second qubit are ideally +1. Yeah, both are either 0 or 1 being aligned. Yeah, and the same thing for qubits 2 and 3. And now if an error happens here, for example, on, say, the first qubit, this will take us out of this code space, yeah, which is the +1 parity eigenspace of all these check operators. And then if we are able to measure these check operators in a smart way, then we can find out about the possible occurrence of errors without measuring the individual qubits, which would collapse our logical quantum state. And then, based on this measurement information forming the so-called error syndrome, we can apply a suitable correction, in this case just a bit flip to the first qubit, to take the system back to the original encoded logical state. Then what we also have for logical operators, like for physical qubits, we have now also logical operators. For instance, a logical X operator, in this case acting as X on all 3 qubits, flipping our 0 logical to 1 logical and vice versa, and similarly, for instance, a Z operator. Now this code is very limited. It can only correct one bit flip, no phase flips. And that's why we have to go to more complex codes, but the philosophy is exactly the same. And this brings me to topological quantum error correcting codes, such as the toric code, which you see here, where again the idea is to store information not in individual physical qubits, but now in collective many-body states of lattice systems of qubits arranged here, in this case on the surface of a two-dimensional lattice. And the idea of topological codes is that as long as noise acts locally on the physical qubits or quasi-locally only in a certain range and not too often or not too strongly, then we can protect the information, detect errors before they kind of accumulate and lead to logical errors on our system. One basic quantum error correcting code of this class is Kitaev's toric code, which you see here. It is based on a square lattice of qubits here, where qubits, physical qubits, are located on the links of the lattice. And now we introduce, as for the 3-qubit code, check operators. Now, however, these check operators are 4-qubit operators that act here, for instance, on all 4 qubits that are adjacent to a plaquette of the lattice. Yeah, on these 4 qubits sitting on the 4 edges here of this plaquette. And these operators, as for the 3-qubit code, will be the ones we measure in order to detect the occurrence of bit flip errors. In order to correct phase flip errors, we introduce complementary operators, so-called vertex operators here, acting with XXXX on 4 qubits adjacent to a vertex of this lattice. Now what you can realize is that all these operators mutually commute, meaning we can measure them without destroying the results we have previously gotten by measuring another one. So that means that we can again, like as for the 3-qubit code, define valid logical states as +1 eigenstates of all these stabilizer operators. Now we place this system for the moment in our head we introduce periodic boundary conditions, yeah, and this is what leads to this toric geometry, meaning that this right boundary corresponds to the left and this lower boundary to the upper boundary. And now what we have in this code are also logical operators of Z and X type that allow us to lift the degeneracy in the code space and introduce logical operators. These commute with all the stabilizers. That means we can apply those without introducing errors. And they mutually anti-commute here, for instance, a logical Z operator with a logical X operator going around these non-contractible paths on the torus. And you see that they anti-commute because they cross in one or more generally an odd number of points. And this is exactly the right kind of maths that we need and that we know from our physical qubits, but now elevated to the level of logical qubits. Now, ideally, we want to have a system without errors. If, however, errors happen on a system, for instance, a bit flip on a physical qubit here that I show in black, we'll again see this by parity changes, where this now even parity is changed to odd parity on the neighboring plaquettes of the lattice, as I show here by this red kind of stabilizer excitations. And again, seeing these stabilizer excitations forms the error syndrome. This is the information that we use in order to guess to the best degree we can by using a so-called decoder of what a most likely error class is that has happened on the system and apply a suitable correction to hopefully bring back the system to the original encoded logical state. Now, we have to be careful. We can't directly measure the physical qubits, as again, this would collapse our encoded quantum state. So we can do this in an indirect way, getting this error syndrome information by coupling the data qubits belonging to this, for instance, this vertex operator to auxiliary qubits by coupling them with entangling gate operations. And then what you see is that errors that might have happened on the system here will flow and onto this auxiliary qubit and be detected there. And that's how we can, in this indirect way, via auxiliary qubits, access the stabilizer information that we feed into our decoders. Now we can ask ourselves, well, how well does our hardware have to work? And this leads us to the kind of threshold for surface code or toric code quantum computation. If we assume that all these gates that we physically have to do in order to measure the stabilizers are faulty, qubit initialization, entangling gate operations and measurements here, for simplicity, at a certain error rate p, then one finds that as soon as the physical error rate is around 1%, one can win this game and detect errors faster and correct them faster then they reappear on the system. And what this means is that these are the error rates where experimental systems are already right now, and that means that by using this approach, we might be able to do fault-tolerant quantum correction in practice. Let me pause at this moment for a second and ask whether you have any questions. If not, then I would now move on and tell you a little bit of how to do this in practice. And at this stage, the more experimentally inclined people in the audience might have become a bit nervous, yeah, because I've been drawing these torus pictures with qubits sitting on the surface of a torus. That doesn't look very experimentally feasible. However, the good news is we don't need this. Yeah? There are also planar versions of these topological codes, of these lattices that can be really embedded in a planar 2D architecture without any periodic boundary conditions. And here you see kind of the smallest version of such a planar so-called surface code formed of 9 data qubits. That's the smallest version that can correct a single arbitrary error. And then these data qubits are equipped, as I showed you, with additional auxiliary qubits here that are used to measure both the parity of Z operators and of X operators in order to detect bit as well as phase flips on the code. And now, we have a few years back, we teamed up with Andreas Wallraff's team at ETH Zurich that are building superconducting qubit-based quantum computers. And they implemented here in a superconducting qubit quantum processor this surface code with 17 physical qubits for the first time. This is called surface 17, 9 data qubits plus 8 ancillary qubits to detect the possible errors on the system. And this is a system that is powerful enough to correct any physical error happening on any of the data qubits, but also during the quantum error correction itself. For example, if a bit flip happens, let's say on this upper qubit, this will show up again in parity violations here, for instance, of this neighboring plaquette here. Whereas the other plaquettes look good, and again, this is the information that is kind of being fed into a decoder. Here, kind of you see the transition from the theorist's cartoon to an actual superconducting quantum chip, where you see the superconducting qubits here as little yellow stars sitting on a two-dimensional chip architecture, which where the qubits here, data qubits, can be coupled by these coupling elements to adjacent nearest neighbor auxiliary qubits, yeah, that are being used to read out this stabilizer information. And then you see this kind of flux lines coming from the outside that are used to initialize qubits, drive single as well as entangling gate operation, and read out the quantum state of the auxiliary qubits and at the end of the entire system. All right, then a little bit more detail. Here again is our stabilizer readout block. And here you see kind of the music sheet that the experimental colleagues then play over and over, yeah, where data qubits are coupled with entangling gate operations, in this case Control-Z gates, but it's a technical detail. Here 2 auxiliary qubits, these, for instance, these 4 auxiliary qubits to measure the Z-type stabilizers. And then afterwards, those are being read out. And in order to do this as quickly as possible, the experimentalists, they use this pipelined approach where they use the time where one type of stabilizer is being read out to map the other type of stabilizers, the X stabilizers, to another set of auxiliary qubits at the same time. So to really minimize the time and perform this quantum error correction in the shortest time possible to keep up with the errors. And this was possible here with about a microsecond of QC cycle time. Here you see then the results of this experiment, where now up to, in this case, 16 rounds or so of quantum error correction were performed, where you see an initial logical, in this case, plus state initialized, and then over several rounds of quantum error correction, what you see is that the quality of the encoded quantum states decreases slowly, and that is kind of an important aspect, yeah, that people often also kind of overlook, yeah. Even if you work with quantum error correction, our qubits die. It's like for us, yeah. We all have to die. The question is whether, if we are ill, it is a good idea to go to a medical doctor that is also doing some errors from time to time, and that prolongs our lifetime, or we better kind of keep our hands up and hope for the best, yeah. And the same holds true here for quantum error correction on faulty hardware, where in this case, the encoded logic information with the error correction still decayed slightly faster than if the information is stored just in a physical qubit. But that is very, very close to the point of break even, and it was the first experiment doing repeated quantum error correction with the surface code, and that is definitely a major achievement towards keeping logical quantum states alive. Then more recently, you might have seen work by Google, where they went 1 or 2 steps further, if you like, and worked now with a larger 2D quantum chip that is able not to host only this 3x3, distance 3 quantum error correcting code, but now also distance 5 and distance 7 versions, yeah, where you see now the number of physical data qubits increases with the lattice size or the lattice length squared, and also then accordingly the number of Zurich qubits to measure the parities. And what they now showed essentially just 2 months ago is that they were able to operate now distance 5 and distance 7 codes here, where you see here now the logical error probability accumulated over many error correction cycles. Again, you see that overall there's still an error incurring, but what you now see here very clearly and distinctively for the first time is that when you scale up the system for from a distance 5 code to distance 5 code, you can ask, by how much do I suppress the logical error rate? And this is measured by this improvements factor that was clearly now here larger than 1, showing that this experiment now operates really below the critical threshold that I introduced earlier, where quantum error correction is beneficial, and we start winning by doing quantum error correction rounds when we increase the lattice size of this system. All right. Yeah, this is how we can. This is the way in which we can do keep quantum states alive. But eventually, of course, we want to build a quantum computer to run quantum algorithms, as I motivated at the beginning. So let me then talk a bit about how we can do actually logical quantum gate operations. And for this, let me change gears once more and change the code, if you like. Now working with the small quantum error correcting code that belongs to the class of so-called topological color codes. So I don't want to go into all the technical details, but what you see here is that the minimal system now consists of 7 physical qubits that are again arranged around in a 2-dimensional planar architecture or layout, where we have 3 X and 3 Z type plaquette operators for detection of bit and phase flip errors. And by little counting of 7 physical qubits and 6 constraints, this shows us that we can again store 1 logical qubit in this smallest topological 2D color code. This is a distance 3 code, meaning that is the smallest weight of logical operators acting on the system, and it tells us that we can again correct 1 physical error on any of the physical qubits. Okay, kind of to get warmed up a bit with this. This is here kind of a cartoon of actually experimental data that we took now 10 years ago in an experiment in Innsbruck, where a logical 0 state was encoded, and you see all the stabilizers, ideally being plus up, plus 1, are not quite at 1, but they are positive. And now if you, for instance, see this syndrome here of 2 of the plaquette operators showing negative sign, and the green one looking okay, this is again the error syndrome that we can take to detect the presence of any error. Anybody brave enough to guess what has happened on the system which of our poor physical qubits has suffered an error? The qubit 2 has flipped, yeah, and by which type of process? That's the bonus question. Yeah, the Z stabilizer is negative. From this we see that it must have been a bit flip, yeah. And but you get the idea. Exactly from this, we can find out where errors have happened on the system and whether it was a bit flip, a phase flip, or a combination of both. Yeah. All right. Now what we did now more recently is to implement this code, or actually two copies of this code, in a trapped ion quantum processor that you see here in a cartoon version, where trapped ions are forming this Coulomb crystal in a 2D. In a 3D trap here, in a quad trap, where they form these crystals, and what you see here, these blinking points, are really individual ions, each of them being 1 charged atom at a time, where you see now quantum jumps happening between the 2 qubit states 0 and 1. If a qubit is in 1 state, it shows this fluorescence light, we see it as a bright spot, and if it's on the other hand in the 0 state, it's dark, so it's still sitting there, but we can't see it. And this is, I think, beautiful quantum optics experiments showing really the actual occurrence of quantum jumps in a system. But it's also very useful because this is the mechanism in which we can use to initialize and also read out the physical qubit state at the beginning or end of our quantum computation. And then by applying tightly focused laser beams to individual qubits or pairs of qubits, we can then use the vibrational modes of the ion chain to mediate entangling gate operations and realize quantum gates between any pair or even larger groups of qubits in this Wigner crystal. So this is a quantum computer with very nice properties in the sense that we have all-to-all connectivity with high fidelity operations. And now, whereas a few years back this was still on messy optical tables, this is now here a picture of this rack-based implementation of such a quantum demonstrator. All right, now what we can do is we can take this and now embed two copies of our topological 7-qubit color code in this linear string of ions. And what we want to do now is, and let me come back to one more conceptual slide, is that we want to run now quantum computations on these logical qubits. That means we have to kind of initially encode our quantum states here in a register of physical qubits, realize logical quantum error correction cycles as I've shown you before. And what I want to focus on now are logical gate operations on individual qubits, but also between logical qubits here in order to realize non-trivial quantum computation. And we have to do this in a fault-tolerant version, fault-tolerantly meaning that we have to prevent errors that will happen when we carry out this information from spreading out in an uncontrolled way of our register. A little bit more formally, what does this mean? It means that if we have a fault-tolerant version of some fault-tolerant sub-block in this algorithm, it means that any single error that might occur, for instance during the encoding here, will only result in a single error, and that is an error that will be corrected by the next round of error correction. So we can tolerate this, and we can anyway never avoid this to happen. But what the good news of this type of fault-tolerant construction then is that the logical error rate of this encoding block, for instance, will scale at least quadratically with the physical error rate, because any single error is correctable, and we need to be unlucky and two elements in our circuit have to fail, and this is a process that happens with p squared. Now what we then see is, if this happens with p squared, then we have the guarantee that at some point we will be doing better as long as the experimentalists manage to decrease the physical error rates to low enough p-values. We will be able to outperform quantum computations on physical qubits. On the other hand, if we, for instance, have a non-fault-tolerant operation of a logic qubit, that's a very bad idea, because then what you see is that single errors will propagate and result directly in uncorrectable logical errors. And that is happening with the probability linear in p at actually several positions here. And then you see, no matter how hard our experimental friends will work, we will never kind of be able to beat the physical qubit. That is why it's so important to work with fault-tolerant quantum circuit designs when we operate our quantum error correcting codes. Okay, then to make this a little bit more concrete, let's look into a concrete example of how we can now fault-tolerantly encode a logical state. What you see here is 7 qubits of our 7-qubit color code, and we realize a unitary circuit, and if everything works perfectly in the circuit, we would be preparing here a logical zero state, as I've shown you before. However, now what you see is if there's a single bit flip happening, for instance here, during the encoding sequence, this would propagate through a subsequent gate onto 2 physical qubits, where it would be resulting in a logical error because our 7-qubit code can only correct for 1 bit flip. So we have to prevent this, and one way of preventing this is to render this circuit now fault-tolerant by introducing one additional auxiliary qubit that is called a flag qubit. And the idea here is that this additional verification circuit is constructed in such a way that any dangerous way 2 error configuration that might come out from a single error here, from this encoding part, will also trigger this flag, and this is like a warning signal telling us, hey, you should not trust this encoding step, you better restart until I, as the flag, tell you everything looks good. And then you have the guarantee that as long as only a single error happens in this composed circuit, you will end up with the correct logical state up to a single correctable error. That's the prediction, and here on the right side you now see the experimental data and results from theoretical simulations we did in my group, where you see you get the ideal state here with, let's say, work with on the order of 90% probability. There are single correctable errors, but now working with this complete block, including this verification step, you see that now the uncorrectable way 2 errors are strongly suppressed, and that is really the signature of a useful fault-tolerant circuit design that outperforms its non-fault-tolerant counterpart, showing that this is already useful today. After having encoded our logical qubit, we want to do gate operations. And a nice property of the 2D color codes is that we can do many logical gates in a very simple, so-called transversal way. So transversal means if I want to do a logical Hadamard gate, taking a logical 0 state to a plus state, I can do this by simply doing physically the respective Hadamard operations on our register of qubits. And that's experimentally very simple. It's single qubit gates. It can't get easier than that, so to say. But more importantly, it's also fault tolerant by construction. Namely, if any of these gates fails, it will again result only in a single correctable error. This transversality also holds for two logical qubits. When we want to realize a C0 gate now between logical qubits, we can again do this by bitwise C0 gates between all the pairs of physical qubits. And you can easily again convince yourself that this is also fault tolerant. If a single bit flip, for instance, happens, yes, it would propagate to a second physical qubit, but only into one error on each of the codes, still remaining a correctable situation. And in the ion trap architecture, we now realize this on a 16-ion processor, operating encoding first two logical qubits, bringing one with its transversal Hadamard gate into a logical plus state, and now using then the logical entangling operation to create now an entangled state of logical qubits, where you see here the experimental fingerprint in the sense of a reconstructed logical Bell state with, in this experiment, 75%, but you should keep in mind this is now not physical Bell pairs, but it's logical entangled Bell states. Now with this we can do Clifford gate operations. This unfortunately is not universal. We can't freely program a quantum computer only from these operations. We need also one non-Clifford gate operations, such as this T gate, which corresponds essentially to a 45-degree rotation on the, in this case, logical Bloch sphere. And if we also have this, if you remember my first slide, on these three gates together, we can program any quantum computation that we want. Now the bad news is that there is simply no quantum error correcting code where we can do a universal gate set transversely in this direct fault-tolerant way. And it was until recently believed that the only way to get around this is to do magic state preparation and injection. And then only recently people came up again with the idea of these flag qubits to come up with more efficient schemes to prepare fault-tolerantly magic states and injection. And we worked on these schemes and adapted them to the Tredian quantum processor. And I want to give you just a glimpse of how this now works. So the idea is we need a so-called magic state, and that's a resource state that you can think of as pointing on the logical Bloch sphere, kind of not along some of these axes, but in this case here in the direction in this plane of the X and Z operator. And this particular magic state, it's an eigenstate of the Hadamard operator, because Hadamard exchanges X and Z, and you see if a state points in this direction, it remains there when I apply a Hadamard. What is the idea of how we can now prepare this logical magic state fault-tolerantly? Well, first we encoded non-fault-tolerantly as before for the Pauli states, and now we can transversally measure the Hadamard operator with these two auxiliary qubits here. And then there might still be errors uncorrectable errors present on the system, and those will be detected by measuring all of the 6 stabilizers in a fault-tolerant way. And only if all ancillary qubits tell us, hey, things look good, we accept this state, otherwise we repeat. And if all flags give us a clear signal, then this is a way of preparing fault-tolerantly this logical magic state. And here you see again, if you work non-fault-tolerantly here with this very simple circuit, it's pretty bad. 10% of error at the logical level. If we now use, however, the full fault-tolerant sequence here, we get the logical error of the accepted magic states down to about a percent level. Again, showing the power of these more complicated but fault-tolerantly designed circuit structures. Now that we have this magic state, we can use it as a resource. It points in this direction. And now by a quantum teleportation protocol, we convert this kind of 45-degree angle in the state into a 45-degree rotation on a target logical qubit. That's what magic state injection is about. It's about coupling this magic state in a transversal way by the entangling gate I showed you essentially to a target logical qubit that can come in an arbitrary state. We measure this state. It will be kind of eaten up in this process. And then besides a conditional Clifford operation, but then realizes this logical T-gate now, converting this into a pi/4 rotation on the logical blob sphere. And here again, you see then the experimentally reconstructed logical process matrix showing for the first time a fault-tolerantly injected T-gate on any physical architecture. And this is really exciting because it's now for the first time that on a logical, complete universal logical gate set has been realized on any quantum code, on any architecture. And this now opens the door to a new era where we can now think of how we can run quantum computations, not on physical qubits anymore, but on logical qubits. All right. Then in the remaining perhaps 5 minutes or so, I would like to conclude by mentioning a few other approaches and what else is going on, and then start a discussion with you. All right, let's look at scalability. Now we've talked about this pretty small quantum correcting codes, and of course, in order to increase the robustness, we have already seen we have to grow these codes, as you've seen in the Google experiment. But we have also need, if you think, for instance, about a solid-state architecture, now ways of having these two-dimensional codes here and coupling them. Let me not go through the mathematical details, but give you kind of the idea. When we want to entangle now patches of logical qubits in a 2D architecture, we can do this by a technique that is called lattice surgery. And in a nutshell, the idea is that we can use an auxiliary logical qubit, kind of knit these two codes together by doing measurements at the boundary where the logical operators live here, kind of gluing these codes together, entangling them. And if we do this in the right basis, and then finally read out this auxiliary qubit here, then we can effectively teleport now entanglement and realize entangling gate operations in a purely planar 2D architecture with only local operations between our physical qubits. And this is something that then, as you can easily see, is if you work with large enough codes, with low enough error rates, then in principle we can do arbitrary quantum computation and scale in a purely 2D architecture towards a scalable quantum computing purely in 2D, which is of course very interesting for a number of in particular solid-state-based platforms. This is something that we're actively working on with our experimental colleagues in Zurich on now coupling surface codes here together by lattice surgery, but also with the trapped ions in a consortium led by the University of Innsbruck, Thomas Mons and colleagues. We are working on lattice surgery between these color code qubits I introduced to you in order to scale systems up and realize entanglement and eventually also logical gate operations between logical qubits. I showed you the way of how we can get to universality by a magic state injection, and that's the most well-known way. However, there are other ways, and one is based on so-called code switching. So as explained to you, there's no quantum correcting code in which we can do a universal gate set fault-tolerantly, transversally. Here, for instance, we needed the magic states, or we can't do the T-gate fault-tolerantly. However, there are other codes, such as 3D color codes, in which we can do the T-gate transversely bitwise, but then we can't do the Hadamard gate anymore. So there's always one, that escapes your the ability of the code to do this gate transversely. However, the idea then of code switching is that if we have quantum information stored in one code, we can switch to fault-tolerantly map this information into another code, do the gate that we can do there, and then switch back. So that means if you want to run a quantum algorithm here, take your favorite algorithm. Now, if you want to do this on logical qubits, the idea is that we can operate the gates in one code, switch from one encoding to the other fault-tolerantly, and do there, for instance, then this T-gate, and switch back and forth. And it's something for which we worked out new schemes of how to do this very resource efficiently with fault-tolerant circuits, as we show in this paper. And now recently we also teamed up with, again, the colleagues at Innsbruck University to show this concept for the first time experimentally for switching between a 2D color code and a kind of reduced version of a 3D code. Let me kind of skip here the details, but kind of give you just a glimpse of the experimental results. What we start in here is a reduced version of a 3D color code that's living on just 10 physical qubits. On this code, you can do a T-gate in a fault-tolerant way, and then afterwards, if you map then this into the 7-qubit color code I showed you before, that's the code in which we can do the Hadamard gate transversely. And then you see that now we can here really apply gate operations T and H on logical qubits, and then you see you can access states here you would not be able to access with only one gate alone, and this is towards covering the Bloch sphere now more densely, and it's the signature of universality. Similarly, we can then also, after the switching, combine it with a second logical qubit. Let me not go into the details, but then kind of show you that we can not only prepare this Bell state of logical qubits I showed you before, but also some non-Clifford distorted Bell states, if you like, by really combining now our gates HT and C0 at the logical level into small universal quantum computations. One additional idea I want to very briefly at least advertise to you is, so far I've shown you of how we can do these operations, and we have to do measurements via auxiliary qubits to detect errors that happen. However, measurements are really kind of the bottleneck in many physical architectures. Often they are much slower than physical gate operations, or they can be even destructive. If you measure an atom, with a good chance you will lose this from your optical tweezer, for example. And also what needs to happen with these measurements is you have to feed it into your decoder. Your decoder has to be really fast enough to keep up with your quantum computer, which is non-trivial for platforms such as superconducting qubits that have a very high clock rate. So the question is, can we get rid of the measurements overall and the classical processing and just have a fault-tolerant yet autonomous and universal quantum computer? And the answer that we very recently found is yes, where we now essentially came up first with a scheme where we can do quantum error correction without any measurements, by essentially, if you come from a physics background, by engineering a very structured open system dynamics, that extracts entropy from our system, corrects errors, however in a fault-tolerant way where we avoid that this noisy process here introduces more errors than we actually correct. And that's again the challenge is to get this done in a fault-tolerant way. Let me not kind of go into the details here, but here you see an example of how this can be done, where we have a logical to be corrected error. Here, say 7-qubit code. We work now with auxiliary qubits here, to which we couple with gate operations. And then the only operations is that we have some reset operations or enough ancillary qubits. And then we see here there's some Toffoli type kind of feedback that we apply in a very structured way in order to correct errors that might be present on our code here in this fully coherent quantum manner. Yeah? And this is an ideal architecture, and we worked out schemes of how this can be done. For instance, in neutral atom tweezer arrays that you see here, where atoms can be held in optical tweezers, can be brought together and excited to Rydberg states to realize gate operations as pioneered in several groups, but for instance in Michalukin's group in Harvard at the moment to a very advanced degree. And now let me skip this part that is on how well this works, and comment very briefly on a very recent work from our group just 2 weeks ago, where we now even went one step further and did not only want to preserve quantum states, quantum memory setting in a measurement-free way, but also wanted to do universal quantum computations without measuring our data qubits at all. And here you see kind of the cartoon version that we guide you a bit through some qualitative ideas. We have here logical qubits. I've shown you of how we can do these transversal gate operations, and I've shown you briefly now of how we can, even without measurements, do fault-tolerant quantum error correction cycles. Now, in order to do a universal gate set, we use the code switching I showed you, and for this we developed now new protocols where we can do this code switching just again by autonomous, measurement-free, and fault-tolerant dynamics, essentially switching without measurements from one encoding to the other, where we can do a T-gate and then switch back. And this is then, again, like I showed you before, how we can get universality now without any measurements. That's the one ingredient, and the other ingredient is we really want to bring this to the regime where we can suppress error rates to the regime I showed you earlier, far beyond what we can achieve with the distance-free small-scale code. And here the idea is that we managed to construct a type of code concatenation scheme where each of these qubits now is again encoded in a code itself, and by this kind of encoding of codes and codes and codes, you can suppress the errors further and further. And this is kind of what you see here, that each of these blocks again is a logical qubit, and with that we can suppress logical error rates to a regime where we can in principle realize now useful quantum operations. Let me skip the details, just give you the idea. Again, this is a fully fault-tolerant and autonomous way where we just use enough ancillary qubits, and kind of as a take-home message here, we looked into the regime where this might be useful, and it's actually useful on various platforms where the idling times during measurements are long, where qubits dephase, measurements are slow, and that is where you should be, or you can be using these measurement-free and now universal quantum computing protocols. Very briefly, there are different aspects we are working in my group on. I just want to mention them very briefly. One is fault-tolerant compilation, where we use machine learning techniques, for instance, reinforcement learning, to come up with better circuits of codes, for instance, on specific hardwares that might not be directly related to actually the code that you want to be running. And that is something that we worked on and still are working on with Florian Marquardt and Robert Wille, for example, in Erlangen and Munich. And then we're also working on new quantum error correcting codes, because as nice as the topological codes are that I showed you, they are very resource hungry. We need a lot of qubits in a plane to get just very, very few, very nicely protected qubits. And there are other codes, so-called quantum LDPC codes, that in a nutshell promise you more and more robust logical qubits with less of your precious physical qubits. And there we have been constructing new code families that have very promising properties, in particular in the near-term regime, where we have not non-asymptotic results, but really code variants with distance 3, distance 5 that work with a few tens or hundreds of physical qubits. All right, with that, let me wrap up by saying, or by showing you one additional slide where we stand, or what perhaps the arguably leading platform at the moment is. Some of you might have seen this. For neutral atoms, a team around Michal Lukin at Harvard has now built a logical quantum processor, similar to the picture I showed you before, where you have now these logical patches of qubits that you can bring together, you can entangle them in a way and run now first logical algorithms. And you see here kind of a cartoon of how this works. Yeah, these patches here are the 7-qubit color code I showed you. They are now being moved around. Yeah, the atoms are being moved around, brought together. Whenever you see these red circles, they are being entangled with Rydberg gate operations. And then what you can now start to do is run now logical algorithms, as this algorithm shown up here, but now on several logical qubits. What they managed to do is to go up to 48 small logical qubits, not doing full error correction yet. These are small error detection codes. Not yet universal, so they don't have HT and C0 in a whole, as I showed you for our trapped ion demonstrations. But what they showed is that if they now use these quantum computations on these error-detected logical qubits, that they could outperform the best physical qubits in their architecture. And this is really important because it's kind of NISQ, but you see, if we now transition to small, not yet fully and large-scale logical qubits, we can do better than what we can do if we run quantum algorithms on physical qubits. So I think that's super exciting because it shows the NISQ era is slowly perhaps coming to an end or transitioning into the era of early fault tolerance, with a lot of interesting and important challenges being open. If you want to join the effort, please get in touch, or you know somebody who wants to join. I hope the take-home message is clear. Fault-tolerant quantum computing is starting today, and it's becoming useful today, and not in 20 or 30 years. And I think there's a lot of exciting theory and also experimental progress. With that, I want to thank very much the fantastic group that I have in Aachen and Jülich. Thank our funders for the support. Thank you for your attention, and say a big thank you to my quantum error correction collaborators. With that, I'm happy to answer any questions you have.
Yes, thank you very much for your presentation. We are now open for questions, as you said, so please feel free to ask questions. So I can also start with one question. So if you now look at current hardware developers, and we want to implement some surface codes, for example, so what are now the main tasks they should tackle, like more connectivity or just higher, better error rates?
Both would be my answer, yes, yeah. I'd say if you think about surface codes, which are of course mostly suitable for instance, superconducting qubits, where you have typically nearest neighbor connectivity, there are already efforts going on to also build long-range couplers between qubits, because this is what you need if you want to get into the quantum LDPC code business. Yeah, which allow you to, as I briefly showed you, to operate with more logical qubits with the same number of physical qubits than by using the surface code. So this non-locality is a very powerful tool, but of course you still have to work on your gate operations. And if the physical gate operations, if you win there, everything that you win there will be extremely beneficial in terms of the resource overhead that you need for quantum error correction. You have to be below the threshold, but the further or the deeper you're below the threshold, the less resources you need in terms of overhead, in terms of the size of the codes you need to reach a certain logical target error rate.
Yeah, so I have a question with respect to the Surface 17.
Yeah.
You showed how the lifetime of the qubit is decreasing as a function of the QEC cycle. I have two questions there. So one is, so you showed that the lifetime it decohers faster when you do these QEC cycles rather than the bare physical qubit.
That's correct. On the Surface 17 experiment by ETH, this was still, not quite at the level of where it became beneficial, but with roughly an improvement factor of a factor of 2. If kind of the 2 qubit gates can be improved by a factor of 2, then you get into this regime where it becomes beneficial. And this is more or less, there are additional improvements, of course, that the Google team did. But this is the main improvement that allowed them, or one of the main improvements that allowed them to get into this regime where you were better than a physical qubit. But even, more important than being better than a physical qubit, the real signature is, because there are many ways of keeping a single physical qubit alive, for very long times. With decoherence-free subspaces, you can keep a qubit alive for 30 minutes or so in a trapped ion. The point is that as soon as you touch it and you do error correction, the question is, will the error correction start to be more beneficial when you scale the system up? So the comparison between distance 3 and distance 5 or 7, that's actually this where the main signature of the improvement and being below threshold is visible.
So in that sense, for the other platforms, it's not at all a problem.
What do you mean it's not at all a problem?
When you do this QEC cycles after every, let's say, operation.
No, it's also challenging in other platforms. Let's say for trapped ions, I've not shown this because I want to show a bit about the logical gates, but our colleagues in Innsbruck and also Quantinuum and others have shown quantum error correction cycles also there, where you can read out ions, you can recool the ions. This is all possible. For the neutral atoms, this starts to become possible, as I mentioned earlier. At the moment, measurements in neutral atoms are slow, and you also have the chance of when you measure qubits that you might lose them. But people are very, very fastly working on solving this problem in various ways. For instance, by constantly bringing fresh ancillary qubits from reservoirs, so that you can keep quantum computation alive. And importantly, qubit loss, if you detect it, is another error that I've not talked about. I've only talked about bit and phase flips. But if individual physical qubits are lost from your system, you can kind of bring in fresh ones. Kind of like if your pullover has a little hole, then you kind of, if you repair it quickly enough before it decomposes, you can also correct these type of errors.
Thank you very much for your talk. I have a question that may be a bit annoying because it refers to minor detail.
Go ahead.
It's not the main focus of your talk, but since you have done a lot of work in error correction, you may be the perfect person to ask. So in the beginning, you mentioned Grover's algorithm as a potential purpose to build a quantum computer. So there's this famous work from Google where they discuss that Grover might not be enough to put us over the edge. And they primarily build on assumptions of how the error correction cycle times, how long they are. So do you think this is still valid because it's already a couple of years old, or has the progress in error correction been so fast that, or so unexpected that this is maybe, Grover is still maybe an option?
I think Grover, I think the argument that Grover only providing a quadratic speedup, if you only knew the Grover algorithm, you would probably not be trying to build quantum computers, except for a niche interest in fundamental physics or so, of seeing where we can do it. And I think this is still true, that when we want having this quadratic speedup will not be too relevant in practice if we can, of course, run Grover in the long term and we can speed up exponential search, still exponential search, but with a factor, with a square root in time improvement, we should be doing it. And regarding the cycle times, they have been brought down, not only experimentally, but also due to new insights on quantum accuracy and fault tolerance. For example, what was believed is, I guess you refer to the Fowler paper from 2012 or so, where these estimates are in, that when you have a distance decode, that you have to run d rounds of d rounds of syndrome readout, as I showed you, to determine a correction. But now, more recently, in particular with these transversal gates, people have realized you can bring this, for instance, round to order 1 rounds. Yeah, so there are actually large improvement factors that are relevant in practice. However, I personally still think that, of course, algorithms providing an exponential speed up, and in particular, from a scientific point of view, I think the first interesting applications will be quantum simulation of many body systems. I think if you're physicists, you're probably interested in that. And for this, we also strongly believe that in general there will be no efficient algorithms that can, in general, simulate correlated time dynamics, out of equilibrium time dynamics of interacting systems.
Okay. If there are no more questions,
Can I ask one?
Yes, of course. One more.
So you did mention that surface codes need lots of physical qubits regularly. So how does it scale? It's like these, let's say, some power of the physical qubits.
No, it scales. Let's say the number of physical qubits scales quadratically with the distance. Yeah, so it's really like the length of this lattice squared is what you need. And now I guess what you're asking is of how many physical qubits you need to get a certain logical error rate. And this is essentially determined by how far you're below this threshold. So what if you look into the Google paper, what they showed, as I said, they showed the improvement factor by a factor of 2 when they go from distance 3 to 5, and another factor of 2 in suppression of logical error rate, going to from 5 to 7. And now you can ask, okay, how large has the distance to be in order to get into this 10 to the minus, depending on your application, 10 to the minus 9, 10 to the minus 10 logical error rate regime. Typically, you will be ending up with a surface code with estimates of like a 20 times 20 lattice or things like that. So on the order, roughly of 1,000 physical qubits for 1 logic qubit. That is at the moment very, very costly.
Thank you.
Yeah.
Okay. One last question.
Thank you very much for the presentation. I just had a quick question. I didn't fully understand if in this measurement-free error correcting codes, did you implement this in any experimental platform? How would they compare to the other codes?
Not yet, but we're working together with colleagues, for instance, in Munich, and even also here in Stuttgart. We're thinking with Tilman V and Hans-Peter Büchler, with whom we did this work on the measurement-free fault-tolerant error correction. So we're thinking about small versions of how you can implement, for example, cycles of this type, and then neutral atom quantum processors. The price you pay if you want to do the measurement-free version in general is that the thresholds that you need to achieve with your gates are a little bit more demanding, which in some sense is not surprising, because what you do with measurements is you just read out the ancillas with a few gates and measure. If you can do this fast and perfectly, just do that. Yeah. But if you get rid of the measurements, you see that what you pay is that you have a larger number of actually quantum gate operations. So you need more gates for a cycle, and that's why your physical gates have to be a bit better. But it's not crazily far off from the thresholds that you have in the standard measurement paradigm of quantum error correction.
Okay, then thank you very much again,
Thank you.
Professor Müller, and also thank you to the audience for participating. In our next colloquium on the 21st of November, we will have Professor Dr. Ian Popp from KIT and University of Stuttgart here, and he will be speaking about his research with superconducting qubits. So thank you for your attention and have a nice afternoon.
Thank you.